So the topic today is innovative electromagnetic-based sensor technology and applications. These works has been done by our group from many universities, including KMUTNB and King Mongkut Lat Krabang and Rajamangala University, and also the key university that collaborate with our work is University of Leeds in UK. This work has been granted the research funding has been granted by Thailand Research Fund or TIF of Thailand. So I thank the Ansys and IEMAS for organizing this workshop. Sorry. Do you see slide moving? No answer, right? That means you
yes,
can see.
I can see
Now I can run until I finish. So as we know today, the science and technology have affects the way of life and change the world. And one of the key technology that change the world and way of life is IoT. And you can see now we have smart farm. It's very important in Thailand. We have smart city. We have what we call smart medicine, right? Also smart classroom. So the key elements that use the IoT success is sensors. That's one key element. So today I will talk about sensor. Kind of different. We talk about the electromagnetic-based sensors that may be used for IoT in the futures. Okay, the background is sensor. Sensor is a device that measure the physical quantity and convert to the electrical signal. So electrical engineer can understand and can use that for several applications. You can see a lot of sensors allow you in your car more than 100 sensors, right? In your cell phones, more than 10 sensors. And your home, your office, for example, in air conditions, in your refrigerators, that many sensors in those things, in the airport, in factories, and also in smart farm. So you can see the sensor is very important. So that's why we working for sensor technologies. It show you quickly example of sensor, humidity sensor to measure the moisture and atmosphere conditions, temperature sensors. You may be familiar with this kind of sensors. Soil moisture sensors, carbon monoxide sensors, alcohol sensor, liquid level sensors. Just quick review of kind of sensor that we use for most of application today. Gyro sensors, tilt sensors, vibration sensor, and Hall effect sensor to measure magnetic fields. So why we do need to work on the electromagnetic-based sensors? Because the previous sensor that I show you, all that's working on the kind of what we call is kind of a normal quantity of electricity, right? For example, measure electricity, measure the capacitance, measure the resistance, and convert to the electrical signal. That kind of conventional sensors. See, the conventional sensor cannot do some job. For example, for long range application, if you need to measure the object that far away from the observation point, you cannot do that thing, except you need to make some wire, some electrical wire to bring the signal from the sensor to the observation point. For some application, including the high temperatures, you cannot put the sensor into the furnace, right? It's will be destroyed. For some toxic area, and also some application you have less amount of physical quantity. So we have limitation for those kind of sensors. So also the accuracy and sensitivity are also very important for measuring of some applications. Those sensors have kind of low accuracies and sensitivities. So why? So then we form the group to study the innovative electromagnetic-based sensors. You see the pictures here. We have some example. Some of them are created by our group. For example, gas sensor, GPR, liquid sensors, microwave sensors, motion sensors. So I would like to introduce our group from Thailand. So we got the funding from the Thailand Research Fund from the year of 2017 to 2020. And we study the innovative sensor technology by using electromagnetics. We have 9 researchers. I don't need to mention all of them here, and I guess some of them are also in this room. We have about maybe more than 15 assistant researchers and graduate students. We have a big projects, and in the big project we have some sub projects. For example, we have a sub project for metamaterial based gas sensor, nanofluidic sensors, waveguide sensor for material characterization, motion sensor, moisture sensors, GPR, and also RFID, including the system with the IoT and wireless sensor network. So I would like to have a quick review for electromagnetic-based sensors. The sensor technique that we use that can be a transmission technique, reflection technique, and resonance technique. In the picture, you can see if you use transmission technique, that means you send the signal and then you receive the signal on the other side, and you can characterize the output signal from the system and convert to the physical properties of the objects. If you use reflection technique, that means you send a signal to the object and get the reflection signal, and then you can calculate the reflection signal and convert to the physical properties, also the reflections. If you are in the electromagnetic field, you may understand this very well, right? So we may measure the diffraction, absorption, and scatterings. And also the last one is resonance. I also talk about this. Resonance means we can take the frequency that the physical property of the object will create the different resonance of the sensor, so we can detect the resonant frequency and convert to the physical properties. So this kind of technique can be used for electromagnetic-based sensors. I start from the first one, what we call the liquid mixture sensors. We use for biomedical applications. This one is used transmission technique. The structure of sensor is quite simple. It's a waveguide. You see on the top first picture is waveguide. We can put a signal to input and we can measure the output signal, right? But this waveguide, we make some hole. We call loop slot antenna. We make a hole here to get signal, leakage signal here. And then we put some what we call subsystem here, nanofluidic subsystem here on the top here. And we make some small notch here to put the liquid. As you can see from the top to the bottom here, the first one is a pure waveguide, only waveguide, right? You can see input signal and output signal almost the same. If you see the second picture, because we put some hole here, that means input signal and output signal have some difference. So we can measure the output signal, some different signals. If we put here, we put some subsystem here, also the same, right? We have some small output signal here. And then we can put a liquid here. You see a blue color here is kind of small liquid here. So when the electromagnetic wave come from the input of waveguide and go to these holes, some is leaked and radiated to outside, and some is reflected back and then go to the output port of the waveguide. So we can measure the signal at the output port of waveguide, and then we can characterize the liquid here. So that's kind of simple models and kind of simple structure that we can use to characterize the liquid mixtures. You see some graph here. Start from the top. It's kind of pure waveguide. You not see some loss. Right? The kind of S21 is transmission signal, right? The second one is kind of you have make some holes on the top of waveguide, and then you put some subsystem here. The third line here, the blue line here, and the bottom one here is you put some liquid. So we can measure these signals. You see the detail of the system. I mean the device that we use for liquid characterization. You see here you have waveguide here. We have waveguide. We have the slot. This is a lead of waveguide. That means we put this on to close the waveguide, right? And we make some hole here. We call loop slot antennas. And this kind of isolation layers. And we have the top one is here, nanofluidic layers, and we make up some hole to put the liquid here. The right hand side is fabricated sensors. And then we do some measurement. We design the sensor with the frequency about 90 gigahertz, quite high. So that's we have to take this sensor to measure at the University of Leeds because they have equipment to do this. And then we have the results here. The dot line is a measured results here. Right? The on this side is a percentage of ethanol. We use ethanol with DI waters, and then we mix ethanol with different amounts or percents into the DI waters. And you can see here from 0 to 100% of ethanol. And we measure the value of delta S21, right? And then we can have some here, all the data of measurement. The red line is kind of a fit plot because when we finish the design of this sensor, we need kind of equations to use for the futures application. So that's why we need to fit the plot. So the equation here, the fitted plot, the equation is on the right hand side here. So the first sensors we compare with the previous in literatures. We found that our sensor have quite high sensitivities. We have about 2% the sensitivity. The complexity is very low, right? You see just piece of waveguide. We can make it reusable of this. We just change the nanofluidic subsystem. So the reusability is very good, and also the cost is low, except the equipment because this is kind of prototype. When we make it for real application, you also need to design all the system with a low cost. But now it's just a prototype, so we use equipment in the lab. I don't need to go to detail in the remarks because I speak out all the detail already, right? So I just skip this one for the remark. Maybe go to the second one, the surface height sensor for photoresist film measurement. This one use the technique of reflection. I mean, we measure the reflected signal and use resonance technique, do both, right? So we developed the non-invasive sensor to accurately measure the thickness of photoresist film on the clear glass that's used for electronic process. We show the design of detail. We use a really high frequency in millimeter wave. So this will be useful for electronic process applications. As you know, when you do some process of electronic devices, you have to put the photoresist on the top of the wafers. This time we use glass wafers. And the process is here, we just put the photoresist of SU8 on the top of clear glass and then spin until we get kind of thin photoresist. The kind of substrate you have here, the some properties here, SU8 is here. We have value of permittivities. So for this project, we need to measure the thin film here, the thickness of thin film here. Actually, we have some instruments to measure this kind of thickness. You may use the optical profilometers, but the thing is, because this time we use clear glass, you may get some errors because it uses optical signals. The second one is you can use kind of mechanicals. You have the tip. The kind the tip here, and you can scan the tip on the surface of photoresist. Also, the disadvantages of this instrument is it may destroy your photoresist somewhere on the glass wafers. So that's why we have to do these sensors. The structure of sensor is quite simple. Again, we use waveguide here, but this time we make it short on the right hand side to get a reflected signal back to the input. So we make a hole here, and then we put a glass substrate with SU8 or photoresist on the top. You can see the signal here is incident wave coming in and go, some is radiated outside, pass through the glass substrate and SU8, and some part of signal reflected back to the waveguide and reflected back to the input. The structure is on the right hand side. We may go some details. Actually, we go back on the structure here. On the hole here, we put some speed link resonator on the top. The structure is here, speed link resonators. It cut a hole to allow the signal is passed to the photoresist. So we study and then we fabricated these sensors. You can see the a piece of waveguide here, and on the top we have the top lid with the hole or speed link resonators here, circular speed link resonator here, and we make a shot here, and this part is input of the waveguide. We put a support here, and then we do some simulations with the clear glass, only clear glass, only glass wafers. We measure the thickness of the, not measure, I'm sorry, we simulated the thickness of glass, only glass, by measuring the at each frequency here. We can measure the thickness of the glass here. We have a graph here for simulation of the only the glass. And for the simulations of the photoresist, we measure the reflected signal, but we measure the different frequency, because when you put the photoresist with, the glass wafer with photoresist on the top of waveguide, the signal is reflected back. You get some frequency shift because the SU8 photoresist will have change some resonant frequency of reflected signal. So the thickness of SU8 with the variations of the delta F, we call delta F, that we measure that reflected back from the sensors. So this shows you the graph from simulation. And so we do some experiments again. So frequency is quite high, about 70 gigahertz. We do this in UC of Leeds again. So from the experiment, and we compare to the equations, we found that if you take a look here, is a glass thickness. Only glass thickness, I mean a wafer, glass wafer thickness. We compare to the equations. I'm not sure equation. Let's show equation from simulations and from measurements here. It's very close. We have some very small difference here between simulation and measurement results. And also this show you the experiment result of photoresist thickness. We show this with the what we call a commercial tool from Alpha SEP IQs. The photoresist that we measure from this commercial tool is here on this block, the blue block here. And the photoresist that we measure from our instrument here on the red block here, it still have some difference, but very few percent that difference. On the left hand side, you see the resonant frequency of reflected signal is shifted, right? So we can characterize the thickness. I mean, we can measure the thickness of photoresist with different delta F of these signals. So we move to the next sensors. Next sensor we would call a sodium chloride solution sensor. Maybe apply for the industrial and biomedical application. This time we use resonant technique. Actually, reflected signal and resonant technique again, right? The structure of sensor is here. We have a resonator is here, and a connector is here. We have the chamber here, and we have here. This is really important here. It's a tube, liquid tube that we put the liquid flowing inside here, pass through these resonators here. So when the mixtures of sodium chloride change, we can see some resonant frequency change here. So we can measure the resonant frequency. That change correspond to the amount of sodium chloride in the waters. So the structure of sensor is here. We have a cavity here, a chamber here, right? And the resonator is kind of post. It's a metallic post here, and we put two in these cavities here. And this is a lid. We put the lid on the top. And the completed sensor is here. We have two ports, port 1 and port 2. And this is kind of liquid tube here. And sensor, I mean, the resonator is inside. So we do some measurement of sodium chloride solutions. We mix the sodium chloride from 1 to 20% compared to the, I mean, we mix sodium chloride with waters. The amount of sodium chloride start from 1 to 20%. So the left hand side is show you the measured setup. So the result is here. The measured result is here. It show you the left graph here is we vary the sodium chloride from 0 to 15. From 0 to 1 to 3 is kind of odd number, right? And we can measure the S11. You can see the frequency shift from about maybe 11 to about 12. And the right hand side is a even number, right? From 0 to 20. The same technique we can measure S11. And they show you the result of measurement. The percentage of the sodium chloride in liquids. On the left hand side, you can see the delta F that we measure from reflected signals. And the dot here is come from the measured results. And the red line, we fit the curve with the third order polynomials. At the right hand side, we use kind of linear fitting curve, right? So that we have two equations for the right hand side, but the same result. From this sensor, we found that for the percentage of sodium chloride discriminations, we can get down to 1%. That's very good you compare to the previous work. And also sensitivity is really high. Fabrication cost is quite low, and also have many good advantages compared with the previous work. So we finished 3 sensor, waveguide sensors. So I think I have about maybe 10 or 15 minutes left. Okay, I will go more quickly. So I'll show you the gas sensors. Let's use the planar circuits. You see, we use the coplanar waveguide, right? And then we put on the top, we call sensing materials on the top. And then when we have the gas contact to the sensing materials, we found that the resonant frequency also shift. We have some shift when the gas contact to the sensing material. You can see on the right hand side here, you can see frequency shift due to the permittivity of the sensing material is vary with the amount of gas that we detect. So the structure is here. We have the coplanar waveguides, and we have some interdigital structure here, and then we put the PDOT as the sensing materials on the top. We call it on the top, thin of PDOT on the top, and then we use for the ammonia gas. So we vary the ammonia concentration from 50, 120, and 5 ppm to 2000 ppm, and then we have a result here. The frequency here, you can see the frequency shift depending on the concentration of ammonia here. The graph is here. So I don't go to more details, so you can see the slide later, because I will give the this slide to the organizer, so you can ask for them later. Another sensor is a liquid sensors, liquid mixture sensors. We use to measure the amount of sodium chloride. Sensor is a planar circuits here. It's a resonators. We have resonator is here. Actually, the structure is kind of like what we call kind of zigzag structures here. Actually, we make it zigzag because we need to make it very small. Try to reduce the size of the resonators. So we fabricated these sensors, and then we use this to measure the amount of sodium chloride, so that when we have here the tube, the liquid tube here, to put the sodium chloride with waters, mixed with waters here, and then we can measure the amount of sodium chloride in the liquid. Again, we can see the result here. The resonant frequency is shift here, depending on the amount of sodium chloride. So I not go to detail for this one. Just show you, we also work for planar circuit sensors. So we come to maybe to the last sensors, we call light paddy moisture sensors. Very important for Thailand because we are the #1 of light export. Milk rice export. Most of the area in Thailand, agriculture area in Thailand, we grow rice. So we need a sensor for agriculture and also the post-harvest processing. You see, this one we will use a sensor for post-harvest processing. When we get the light from the farmers, the moisture content in the rice is very high. The paddy rice is very high. It's maybe up to 30%. We have to reduce before to make milk rice. So this card show you the diagram of factories. We have a silo. The silo will make the light dyes. We put the hot air into the silos and flow the rice from the top down to the bottom. again and again until you get the amount of moisture of sensors below, I think below 15, about 10 or 12% of moisture that you can use for processing of mule lice. So I go quickly. It's not moved. Okay, I go quick. About 11%. Let me show you the picture of factories, the mule lice factory in Thailand. The right hand side is a guy who working on this project. I show you some. We put, actually we need to make the moisture content of sensors in process and real time, and we need to measure the data. I mean, put the data of moisture content via the IoT. So that's why we're working on this one. We hope this one will make the accurate process for making mule lice. Quickly, I'll show you some picture of rice. If you decrease the amount of moisture of sensor, moisture contents from 2014, you see more crack, right? Down to about 10, you see more crack here. So you have to be careful. If you reduce more, you get more crack, and that means it will destroy the mule lice, and you get the low price for your lice. Today we have standard tool to measure the moisture content. We can use the capacitance technique. We can use a resistive technique. But this one, you have to take the sample from the silo and make it outside and measure by this tool. You may get some error when you take the rice away from the silos. So that's why we need to put the sensor just in the process. I mean, beside the silo, that we can measure accurate data from moisture content, and also we can monitor for real time. So we study the characteristic of rice. Here we measure we also measures. We get the data of permittivity of rice, and then we design the sensors here. I have maybe 5 minutes left. The sensor is just antennas. If you in the field of electromagnetic engineer, you might familiar with antenna. These two antenna, we have input antenna and output antennas. And the subsystem here, we have a generator of microwave signal. We have detectors, and we have embedded system to control these signals. I go quick. So this show you the silo. The right hand side show you two antenna. The P1 is power from the transmitters. This go to this. We have a light here between P1 and P2. Antenna P1 and P2, we have lights here. Right? So the signal from P1 go to P2, and then we can characterize the moisture content of sensors, because it's changed with the amount of powers at the output antennas will depend on the moisture content in the lights. Go quick. Not smooth. Wait a minute. Too slow. I go quick, but it does move fast. Okay, no problem. Just some minutes, I can finish. Okay, this show you the real system we put here. I'm sorry, here, somewhere here. And then I'll go quick. You can see the how it operates, right? He show you the real sensors and sensor system here. And then we measure the results of moisture content of sensors, and then we compare with the standard tool. and we have some curve for our system from the we fit from the measured data. So we compare here with standard 2, right? We get some difference. We not call error. We got some difference with standard 2 about 6%. So I would finish here because the last one we use the same technique of moisture content sensor to measure the moisture of soil at the restoration of historic place in Thailand. So, but the same technique. So I would go quick. Yeah. So final remark from me is we develop a lot of electromagnetic-based sensors, including sensor for liquid characterization, the signet of photolysis, and gas sensing, and also the moisture content of sensors for rice and soy in Thailand. Thank you very much for your attention. If you have a question, maybe next session we have Q&A question. Thank you very much for you all.
Thank you, Professor Prayoot. Reminder for the audiences, we will have a Q&A session in the end of webinar. And during that time, I will open to ask questions verbally. So the next speaker is from Ansys company, Desmond, and he will continuously talk about Ansys comprehensive solutions for developing electromagnetic-based sensor.
Can you guys hear me?
Yes.
Just share my. Oh, this is the wrong one. Just hold on, let me just turn on my PPT. Can you guys see my slides?
Yes.
Okay. Yeah. Good morning, everyone. So basically, I'm Desmond from Ansys. All right. I'm the regional technical manager for the Ansys products. Right. And basically, I've been working in Ansys for almost 20 years. Okay. I'm located in Singapore, basically. So I support customers based from around Asia, all right, ASEAN, Asia, China, Taiwan, India as well. So my specialty is actually in electromagnetics, right? More focusing on the high frequency. Okay, but today, pretty much that for high frequency, right, I'm be talking more about using our Maxwell tool to actually, simulate the application for sensor on the magnetic flux type of sensors that we are looking at. So this is my agenda today. Okay, I'll have an introduction on the sensor design suite, then also on basically the sensor part will be more on the automotive applications, right? Which include Hall sensor, variable reductance sensor, magnetic resistive sensor, and flux gate sensor. So let me just don't worry about the products that we have, but just I'm trying to introduce that the optimized simulation tools that we have. We just put into two parts. One is low frequency and one is high frequency. So for the low frequency, basically they are both electromagnetics, but they are different type of solvers that to address both type of applications, right? And we have Maxwell for the low frequency, and we have HFSS for the high frequency. So I've seen for HFSS, I've seen what just now the professor is working on is basically more on the high frequency resonant type of sensor. which is the typical, I would say that you know, in a layman term language is actually all about antennas, all right? Because we are trying to transmit a signal, receive the signal, and from the signal itself, we signal process it and see what is the, you know, what type of sensing results that you require, right? So basically, we can use HFSS for that, for designing antennas. So that is so much about HFSS that I had presented 3 weeks ago on the wireless power transfer, which is the same type of application concept. Right? But today I'll be more focusing on this low frequency on the Maxwell part. Okay. So these are the difference between the two solver. All right, Maxwell is basically a low frequency field simulator. In Maxwell, we separate both solver, magnetic and electric. All right, transient, time transient, and lump circuit for RLC. Then you're able to address linear and non-linear materials, right? Of course, the applications is more on like motors, transformers, inductors for power devices, and also inductive noises. Right. For high frequency, as I mentioned, it's an electromagnetic full wave solver. It's typical circuit for S, Z, and Y. So what you want is more on S parameters. It addresses linear materials, things like antennas, transformer induction for high frequency, and radiations noise like EMI, EMC. Right. So this is about the difference between the two solver. So let's go into more focusing on the applications that we're going to introduce today. So what you see here, I'm going to introduce a sensor for this electromagnetic device that uses a magnetic field for sensing. Okay, which actually we detect the magnetic field of the sensing part from the coil, right? And from there we analyze the different type of induced current, induced inductance, and how this data being processed, right, using our circuit tools as well, our system tools as well. Okay, I'll introduce it when we go on. Velocity sensor for anti-lock brakes and stability control. Position sensor for this static seat location. Right? And we have eddy current sensor for fade detection, right? Where you can have sensor to detect cracks on surfaces, right? That's very important. Where, you know, application can be like aircraft, you know, space shuttle. You need to have this sensor to actually detect cracks. You know, if there's cracks on the surface of this aircraft, right, then it's going to be very disaster when, you know, you fly out of this atmosphere, or the high pressure can actually cause pretty disaster type of accidents, right? So actually from here, right, we see that most part of sensors we are doing here is, we call it device characterization. We device characterize, we put the geometry of the sensor, okay, material property, environment condition, all right, into the solver, all right, into the environment solver. Then you know, we can understand, from there we can characterize the different type of geometry, material characteristics, environment condition, for the most significant effect on the performance itself for the device, for the sensor. Right? Then we have different type of post-processing, like statistical, Monte Carlo sensitivities, and design of experience, where you can actually do several experiments on different type of material characteristic, geometry, to see the optimal design that you require for that particular applications, right? Especially on the sensor, which is very sensitivity. And we also have this optimization tools to define design. Okay, we have algorithms such as quasi-Newton, genetic, pattern search algorithm. These are more on the way the optimized tools you know, runs. Right, so there are different type of methods to do that. Okay, and so basically, after you do these models, you categorize in Maxwell, right, you can actually we call it you know, electromagnetic link or dynamic link into our system simulation, where you can put in all the circuitry, like your feedback circuitry or your control control blocks, right, inside the system to actually mimic the whole system simulations, right? Basically using based on what you have designed on your sensor part. Okay. So basically we have something called sensor design suite, where there's a series of there's a series of related solutions that can assist engineers to design and analyze electrical machines, right? And we have things like libraries and all that to actually support that type of design that engineers require or the company required. Then we can integrate this whole thing, right? Is a single platform that integrates circuitry, electromagnetic system engineering into a environment. We call it electronics desktop. Right? It's just a single environment where you can call in all these components, like from the way you design your structures, your device in Maxwell. You can actually connect them into circuit and all this. So it's actually all fully integrated. Then solution that we provide for low frequency, as I mentioned, we have Maxwell 2D and 3D. So it depends on the structures, right? Because you might want to start out with 2D, okay, because the electromagnetic field basically is static. So, it's in one exit or two exits. So basically you can start out with 2D to actually try to analyze it and see what is the effect that you have for your design. Then you can convert that 2D easily into 3D inside the solver itself. So basically you can do that through and through, right? Then, of course, from there, you can do a steady state solver using DC or frequency domain, transient dynamic solutions for time domains, handling all this time-induced eddy effect, right? Because this is AC current when it comes to eddy effect, right? So basically, you can have DC, steady DC for this steady state solver, and dynamic solver, we can use AC on. Okay, so these come with different type application for different type of solver. So basically, it's all in a single platform. Then in a single platform, you can do optimization on shape, position, when you do, because it's a sensor. So when you do rotation and all that, you can actually do parameterization, right? Design variation, optimization, basically on that particular design. And it comes with something called Simplora. Simplora is actually our system tools where you can actually integrate as I mentioned, your Maxwell, like your Maxwell static models into your system simulation. You can link them together, putting on this different type of circuitry, because your sensor might be running on the IC, that the IC can actually sense out the currents and all that to see what is the inductance and all that. We can actually analyze through using system simulation. It's like a full system simulation that you actually plug in your sensor into the real environment. All right. Then from there, we can concentrate the saturation and the back EMI effect. Okay, and evaluating the design alternative with parameterization, which means that at the same time you can do system simulations and variation of the design. Okay, so this can be done concurrently, and obviously that for Ansys, right, we have very diversified type of solver products. We have electromagnetics, we have thermal, we have stress. So all the structures, especially sensor, right, it can be in a very you might be installing this sensor into a very hectic type of environment, like inside a very high temperature burner or in a rocket where you start to burn off and all that stuff, right? In a very high temperature or very low temperature, you can do a thermal simulation as well at the same time when you have your electromagnetic data, all right? And obviously, when there is a thermal heat that comes with stress, so basically you can actually couple the thermal into your stress and see what are the stress effect on your sensor part. Okay. So this is the full electromagnetic flow, right? Electromechanical flow, right? When you say mechanical, basically for sensor in type of sensors that we are working on now, like Hall effect or barrier reluctance sensor and all that stuff, is actually using the we call it mechanical signal into electrical signal, converting mechanical signal into mechanical motion. I would say mechanical motion into electrical signal. So in the whole system here, right, the heart is going to be a Simplora, because we will put every components into the Simplora and run as a system simulations, right? We don't just when you do a sensor characterization, you don't just design the sensor. you want the sensor to be put into the real environment where you can actually analyze the system as a system level. All right, so that you can know that when you're after you design your components, right, your sensor components can be put into a real system to run it and see what is the effect, and from there you can actually optimize your sensor further, all right, with the real virtual task simulation data inside the system. Okay, so we have other components like ARM Expert, where it's for motor design, because some of this might be, some sensor might be require some motor to monitor the motor stuff and all that stuff. We can have motor design into the system as well. We have magnetic from P Expert, all right. Then we have Q3D for actually parasitic RLC stuff, right? So basically the change of inductance, capacitance can be actually simulated in Q3D, right? Then optimization, as I mentioned, because we are more focusing on Maxwell 2D and 3D now for electromagnetic components. So basically in that part, right, you can do optimization as well. Then we can, from there, we can couple to Ansys mechanical for thermal and stress. And this thermal and stress can be also coupled into the system level. All right. So basically, you're not only design your device in Maxwell to address on thermal and stress, right? But not only the component, but actually in the system level, you can actually address your thermal effect as well as a whole system. So this is we will have example later on to show you what are the. These are just a slide to show you how does the system platform look like. Okay, you see that the Hall sensor models there, and we can actually, the Hall sensor simulated in Maxwell is just a passive component. So basically what you do is after you analyze whatever characteristic that you want on your Hall sensor models, you can actually put it into Simplora and actually run with simple type of current flowing through, how the thing rotate and all that stuff, so to extract out all this magnetic field. So basically this system will be a subsystem of this control of this Hall sensor. Then after that, this subsystem of this Hall sensor, right, can actually plug into a total simulations, right, with the feedback control, the wheels like maybe this sensor is for the rotating wheel of your vehicle, all right, to measure the speed and all that stuff. We can actually put it into the system level. Then we can actually analyze it and see how does the sensor works on a real virtual type of rotation of the wheel itself. Right? Then we can have this rectifier circuit to power up the sensor. We know that a Hall sensor, we have an IC chip inside there. So this IC chip, doesn't matter where you might need, this IC chip is just a simple current sensing. So basically we can have that condition, right, being addressed inside the system level, right, by putting on the control blocks and all that. So basically you can actually work out on this part, right? So basically, because when for people that for customers that actually design sensor itself, right, they are not really concerned about the whole system, because most of the time they are concerning about the structure itself, the sensor itself. So many times when they feedback from customers, right, they have to know what are the applications that customer use so that they can actually sell the components to the customers. So this components designer, they actually need system level simulation as well, so that they know that what type of applications that their customers are working on. And from there, they can also optimize or customize some of the sensor for the customers. Right? So from there, we can actually make use of the system analysis in Simplora to do the system level simulations. So let's start with Maxwell. All right, Maxwell is, as I say, is a 3D solver. All right, for a solver that actually solve separately for magnetic and electric. Right? So basically, there are two different solver. All right, so basically, you can actually solve each of these solver that you require for your applications. So the Maxwell is very simple. You need to have your 3D structures inside, import into the solver, and with the material characteristic that you assign. So it's like an actual thing that you actually design in your real world. Right? Basically, you just put it into a simulations. So as I mentioned, there are different types of solver: electrostatic, electromagnetic, eddy current. There's 3 types of solver inside Maxwell. So it depends on your sensor behavior or characteristic, you can use different type of solver to do that. And transient electric, right? I think the last one is actually the transient magnetic. Okay, so these are all AC, DC and AC. Okay, but both separate solver for electrostatic and magnetic. Basically, is to one is to analyze voltage, the other one is to analyze current, right? So this is actually the what you see here is actually the platform for the GUI for the Maxwell. Okay, when you import in, this is 2D actually. All right, you can actually do in 2D or you can actually create into 3D. All right, it's very simple. It's just one click of the button. And we have this history table that show you, history tree windows that show you all the components that you have inside your models, all right, basically, and you can assign all the materials that you require, and you can have special materials that you want as well, all right. Some of the special materials like ferric materials that you can get from your vendor to actually import inside here as well. So it doesn't mean that you have to use our library. You can actually create your own library for the material. So basically for 3D solver, the 3D solver simulations, right, the most important is your geometry and your material, right? After that, you just assign boundary condition and excitation, then you can, it's that simple. Right, but of course, you must know how to assign your boundary correctly and your excitation correctly. That's it. Okay. Then for this solver, right, we use this proprietary techniques that we have. It's automatic adaptive meshing. All right. So what it does is you can put a criteria that you want to mesh for your your volume loss or your magnetic loss that you want. All right, we have a default value, so it's up to you. Right, you can actually put in more constraint, like more than less than 1% of errors that you want. So obviously that this, when you start off, right, this is actually automatic meshing. All right, so we don't do you can do manual meshing, right? They allow you, the solver, the GUI allow you to do a manual meshing, but for electromagnetic, right, we know that everyone know that you need to know where to mesh, right, in order to get the correct result. So basically, in Maxwell or in HFSS, right, we have automatic adaptive meshing, right, where it actually smartly, the solver will be smartly to know where it need to mesh due to your excitation. So basically, they will know where are the highest field and all that to make a more dense mesh, so that your refined mesh will be more accurate, when it comes to the results. Right. Then this is a typical 2D and 3D results that you'll see, right? Like this is this case, right? For this is just a motor application where you see the tau and this time versus and the winning current with the time versus the time. And the typical result, you can see also animations, right? Field plot, right? And see the field or the magnetic flux that actually occurs on the device itself. And you can plot, by doing parameterization, like moving the teeth of that rotation, right? Then you can actually see what are the difference between the inductance that being induced inside your coil and all that stuff. So you can have different type of current flowing through with different type of how does the inductance being shift, all right? Like this case is a flux gate sensor, so basically you can see that how the inductance being shifted, right, when it has censored different type of currents, right? Different currents on the excite from the external field. So Simplora basically is a system simulations, right? So you can see that just an overview, right? So basically you see this, right? We have different type of solver inside there. We have circuits, right? We have block diagrams and we have state machines, right? Basically circuit, if you have your circuitry, you can actually use the components inside the circuit, right, to connect up the components, and you can actually, with this driver, right, driver circuits, you can actually drive your sensor. If you don't have that type of circuitry, all right, and you have spice model, we can do that as well inside Simplora. But most of the time that those customers or those vendors that design the sensors, right, might not have all this circuitry or might not have the privilege to actually get that type of circuitry from the customers, because these are all proprietary, right? So what you can do is, if you know the condition of how to turn on the sensor, how to between the switching on and off of the sensor, right? You can actually address your circuit by using block diagrams. All right, block diagram is like a digital diagrams where you can actually on and off, or whichever you do a gain, you do a linear. So these are more like a mathematic type of blocks, all right, where you can represent your circuitry. Right? These are more, well, it's more on the simplified, but at least you are able to use it to do your system simulations, right? Basically, so we have this block diagrams inside a Simplora as well. And state machines as well. I don't want to mention that state machine is like a coding machines where you can do a coding and actually by doing some condition and condition to actually activate some of this circuitry inside where you require to require to assess your sensor and see what is the performance of the sensor in the system level. So these are the 3 levels that we have inside Simplora, where you can actually easily connect up as a system level. Then inside there, right, inside Simplora, we can actually link to all other solver like Maxwell, P-Expert, R-Expert, and Q3D, which means that you can bring the whole model of that sensor that you design, right, plug it into your circuitry and run it as a system. Right, I'll show you later on further slides. And the analysis part is basically DC, AC, and transient, right? So we cover all the domains that you require in the system level. So you can co-simulate with Maxwell and Simulink as well, all right, third party, and MATLAB too. All right, if you have MATLAB, if you have some driver circuits that actually design in MATLAB, or you actually have some MATLAB library that you require, you can actually link to Simplora, all right, so as a device, as a component to drive your device. Statistical analysis and optimization. So from this part, right, on the system level, you can also do optimization, right, to optimize your device for that type of condition that you require in the system environments. Then we have this VHDL and AMS capability, but these are more on the automotive, but we actually cater for all this industrial, right? So this is a multi-domain design in Simplora where you can actually put in all this stuff, right? Not only sensor, we have transformer, we have electromagnetics, mechanics, power converter, utility. So this sensor can be part of this environment, where maybe there's a transformer, but you want to sense that the voltage that is transformed, right? You don't want to be out of the voltage. So when it's out of the voltage from the secondary, maybe this secondary voltage can be feedback to your sensor and say that, oh, this is too high, or whether your motor is too hot, type of thing. So sensor can be in different type of applications, right? So basically your sensor can be put into the environments where you can test together with all this, some other devices, right? And this is actually, EC-Link is basically to link to your 3D Maxwell solver. So basically this is just a integration between your Simplora and Maxwell. So nothing much, you just bring your model into Simplora and just connect up inside Simplora. So optimetrics, right? The overview basically, well, optimization is basically one of the requirements that you want for your design, basically, right? So basically when you design when you start to design your structure in maybe your sensor on paper, right? So it's not optimized, it's just a draft, right? So basically when you put this design into the Maxwell, all right, you can do optimization, right? You can optimize based on material. Maybe you want a low cost material, and also you don't want, when you have a low cost material, you don't want to compromise the performance of your sensor. So basically you can actually see what is, how to optimize it to your best, and you can actually balance between the cost and your performance of the sensor itself. So it depends, right? You can optimize the temperature, you can optimize the material, you can optimize different type of shape, that you require, right? So basically optimization is really important, when it comes to design. So you just basically create the original design, which is your draft design and your nominal design. All right, after your draft, your nominal design, which is the design that you want, then you do a characterization, you solve the models. Then from there, you can actually add in some of the variables that you can actually do your optimization or parameterization. All right. So optimization is very unique, all right, basically, because it's something that you require, okay? we can do that in optimization. There is some other capability like parameterization. Parameterization is to actually sweep all the variables that you require. You can state the variables and you sweep all the variables, and you can actually save all these variables so that you can do it. You know, it's like a data collecting. All right, you can have early parameterization of different type of data and keep it, and for your further design, all right, that you want. Then you can do optimization. You can even do sensitivity. Why we need sensitivity? Because, you know, when this device is going to manufacture, right, you want to see whether -5% to -5% to +5% of variation in terms of the process, in terms of process variables, right? How much tolerance can you have? All right, that's very important, because whatever you design is very ideal. All right, but when you go to process, when you go to manufacturing, right, there will be some variables or some micro change in your process when it comes to manufacturing. Basically, from there, right, you can actually do a sensitivity to see whether some of these critical variables that you have in your sensor, right, when you go to manufacturing, does it affect your performance? All right, you still can actually cater for that type of tolerance, right, in terms of going through that manufacturing process. Then you can do a real-time tuning. All right, basically you can tune your variables and see what is difference between different type of dimensions and see the results that you see. It's on time, it's real time basically. Then statistical, you can actually do a distribution. It's like QA, you know, do a distribution like your design output, like your forces, your browse, and your losses, right? Your core loss or your magnetic flux gains and all that stuff. All right. So basically, you can actually do a statistical analysis as well in your models. So I will not go through all this because these are some of the algorithms that we use for your optimization. You can choose to optimize based on this algorithm called Cross-Newton's pattern search, all right? Sequential nonlinear programming, sequential mixed integer nonlinear programming, and genetic algorithm. So basically, you can choose to have different type of optimizer, but this optimizer is based on certain application sometimes, or is based on certain algorithm. You might need to study them to see which is the best, but by default it's quasi-Newtons, which is very general. Then the rest you can actually look up and see whether some of these things might be more appropriate to your design, so you can use that type of optimizer. So this is just a process flow. How does it work for optimization? You know, you start out with design, you simulate, evaluate, okay, yes, then you manufacture. If you know, then you keep on optimizing. All right, that's it. This flow is automatic. All right, it's automatic until it stops and you see your results. Okay. Then let's go into some of this automotive application for, you know, sensor for automation. Let's start with the Hall effect sensor. So it's a speed control. We all know that. It determines the flux crosses the 3D Hall effect sensor. All right. So you can see that whether you can, you know, this is run in Maxwell. So basically you can see that when the wheels rotated, all right, when the wheels rotate, the gap between the sensor and the wheel can be parameterized. All right. You can see that on the left hand side, the sensor can be parameterized in terms of the gaps. Right, it can be far away, it can be nearer. So you can optimize the best locations of that sensor that you need to place. Okay. Then after that, you can rotate the wheels and see what the effect of this magnetic flux, all right, crossing the sensor. So basically, we know that this sensor have a permanent magnet, pole piece, and Hall sensor. So Hall sensor basically is from this IC chip itself. So we will not be able to simulate IC chip inside here, but we can put the IC chip inside Simpora, right? So basically, we are just working on how the magnets be affected by the magnetic flux, you know, when it passes the Hall, the 3D Hall sensor. So from there, you can see the magnetic field, and then we call it ECE connect link. Remember, it's actually dynamic link into the Simpora, putting the whole sensor inside there. Then from there, we can actually build out the system. Right? I will show you in the same. We'll show you in the coming slides. So this Hall sensor, basically, you can actually plot out the flux, and you can see different type of view on the axis itself. All right, you can see how the flux flow and whether it's optimized, and where if it's not optimized, you can do parameterization plus optimization to actually optimize your structures. And also we can see the field in the IC and Hall and a Hall sensor. So basically you can see the normal between them and also the different time axis of the field effect. All right. So you can see that you can actually know and realize where does the field flow and whether is it correct, in the way that you place. And the animation also show you something that very meaningful, because it's something that you won't see in your measurements or you won't see in the actual device. All right, you only see data that coming out from the actual device, but basically in simulation you can actually see more things. All right, you can see how the magnetic flux been induced inside the wheels, all right, and how does the gap affect the magnetic flux, all right, between the wheels and the Hall sensor. And of course we do a parameterization, all right, parameterization between them on the different angles or different gaps, right? You can see that how does this flux being induced, all right, in between the spacing of the gaps, all right? So you can plot out this graph, which is very useful because know that between all these gaps, right, what are the flex characteristics, right, between them. So this will allow you to design or optimize and also to fit the applications that your customer wants. All right. So let's go into a system level. So after designing the Hall sensor, right, you can actually do a link into your Simplera. And this is just a subsystem. Why I say subsystem is because to activate your device, right, by external drives, right, you need currents, you need all this stuff to actually power up this stuff, right? So basically you can use in this case, we're using a control block to do it, right? It's easier. You can even use control block inside there's equation where you can use equation to analyze what are the current you require as a source, right? So basically you can analyze it with equations and import that into your 3D models, right? So and then from there you can have different block and see what is the characteristic and control on the gap itself as well. All right, so you can see that this is like a device, it's like a chat device that is being powered up, actively. Okay. So when you go into that, you can see that with this signal inside there, you can see whether the differential signal is being detected, right? Whether if the space is 3 mm, right, the differential signal is too small, right? Basically, that if it's too small means that you will not be able to detect it properly. So 3 mm is not going to be a good gap space, right? So if we become 1 mm, right, so basically that will be detected. So you can actually parameterize between 3 to 1 mm and see what is the optimized one. So basically you can work out in that case inside doing your simulations, right? Before you go into your actual putting into a real environment to test your sensor, you can actually put into a system level to do it. So you see that this is a rotational Hall sensor where you have different sensor inside that rotatable. So basically you can see that the Hall effect for IC A, B, and C, there's different sensor that we can put that into a system level. In that case, right, we will put that in the system level by using a block diagrams. Basically how to you can see on the side here, we can actually represent the Hall IC A, IC B, IC C, right, into a block diagrams, and actually from there we can actually categorize in the block diagram to come up with the source that you required. All right, then because IC they don't design the IC, they just actually buy the IC and plug into the sensor and design the sensor. So the Hall sensor, basically the IC part is actually could be from their vendors that actually buy and just plug it inside the design. So this either the vendor that can give them a spice model or whichever different type of characteristics models that they can give. If they can't, right, basically you can actually build that in the block diagrams, right? And check what you need is just the source, right, from the IC. So another part of design simulations that you can see here is the animation part for this. We call it string-line plots, right? You can see how the field being immersed inside your wheels and the gaps between them. So This is all very useful information for designer, right? To see what are the material, especially you can see here that different type of materials, different type of magnetic materials or whichever, you can see how strong is the flux is and how it been induced into the environment. Okay. Then the next sensor, right? We'll go into like maybe 4 different type of sensors that have been created in the using our Ansys tools, right? So basically, the next one is variable reluctant sensor, which is actually basically is to the resistive part is from the magnetic field, right? The change of magnetic field actually changes the resistive of that different type of condition. So basically, from there we can actually use that as a sensing part to process the sensing results, right? The sensing data that require, right? So it's for obviously there's a lot of sensors that for different application, but there can be a different type of sensor for one application, like speed control. It depends on what type of condition that they require is inside a car, inside aeroplane, whatever. So sensor can be different type of application for military, from commercial, or even for a small little thing or domestic stuff like maybe a fridge or whichever, inside our home. So basically there's different type of sensor might be using the same application, but depends on that type of products that they require. More expensive sensor have, all this is being is actually in the market. So this is variable reductance sensor. Basically, is for speed control as well, right? By determining the output voltage. Okay. So what it does is consider the various flux linkage versus time, due to non-linear materials, fringing, speed of the rotation. So it consists of magnetic, permanent magnetic coil, poles piece, right, where it's south poles and for the magnet itself. And it's actually same thing. Is placed close to the wheels that you want to analyze, and also that the gap is actually important as well for these characteristic variables. So you can see, you can rotate the thing and you see that the flux between them that induce, right, and the flux changes, right, basically is the resistive part of the magnetic field that change, right? So basically it can actually allow that type of change to actually convert to voltage. So if you see here, right, again, that part of this characterization in Maxwell, right, of this variable reductance sensor is being imported into Simplora and build a small drive circuit to drive this sensor, all right, basically. So we have these components, source components, resistor, resistor components. We can actually plug in and connect them into this 3D components. 3D sensor. Then from there, we can analyze it and see the angle versus time, and also the output voltage versus time. All right, so basically you can see from there and how this thing being moved. So whatever you have been optimized inside a device will be actually so-called monitored here. All right, basically in your voltage and your angles. Then the next one is magnetoresistive sensor. This is a more complex one. Basically, the application is more on this. I would say that more military as well, right? For this case, it's a speed control for gear wheels, right? Basically, what it does is it based on the resistance change with the angles, right, of this magnetic field that crosses the direction of the current, right? So basically, what it does is when this magnetic field changes, right, then the current flow through actually, sense that type of resistive change, because when the current flow through and the magnetic field being actually distorted on the teeth itself, right, on the wheels itself, right. So this changes, right, actually reflects to the resistive. Okay, so they uses a Maxwell to actually determine the average magnetic field angle, right, for alpha. So with this case, right, we can use Simplora to act like a lookup table, all right, for this angle, the magnetic field angle, versus the rotation gives us the resistance, right? Because the rotation actually changed the magnetic field angles, and actually there's a change in this resistance, right? So from there, we can actually come up with this equation. This is a common equation: R equal to R naught plus angle R cosine squared alpha. So basically, this equation can be plugged into Simplora and actually to analyze that and come up with a table. All right. So this what it does is we do that in Maxwell. All right. Obviously, for the models, the input parameters will be the rotation of the angle of the wheels, all right, and the permeability of the missing tools, all right, because we want to sense whether there's any missing tools or not that in a gear, right? So basically, you can see that we can do that by doing some setup in the Maxwell. Okay, so this model will be actually later coupled into this model after analyzing, right? In Maxwell, we have something called field calculator, where you can actually calculate certain point of the structures that you want, like your alpha, like in this case is alpha tangent, we want to get the alpha, right? So basically, based on the equations, right, we can actually plug R equal to R naught and angle R cosine squared alpha, right? So we can actually plug this inside the field calculator and actually put in the geometry, right? The point or the geometry can be a line or it can be a cutout face to calculate the volume or the scalar of this alpha. So basically, you can plug the equation inside there and actually calculate a single value that you require. So this single value can be parameterized in the way that different steps or all that, and you can collect all this data, right, and plug into the so-called this lookup table. And you can export out this lookup table. This could be some a bit of manual, but what it does is you can export out these tables and you can actually manually process inside a tool like Excel, all right, to analyze the data, not just to formalize and process the data, and actually export back to the import table and put into the Simplora to run as a system level. So this is some of this flow that we can do, on the system level, right, by using Simplora. And as usual, we can plug all this field and see, right, basically. So you can see that this sensor basically magnetic sensor are more the applications, the structures could be the same, but the analyzed part could be different. All right. So basically you can use Maxwell to actually analyze all these characteristics. Then also, the alpha and the missing T, that from 15 degree, right, and 30 degree, you can see the sinusoidal field, sinusoidal curve that you plot inside Maxwell or inside Simplora. It can be different type of shape and you can analyze from there. So you see here, right, same thing, the MR sensor, which is as what we did on the Maxwell. We can connect up into the Simplora and drive the sensor, and whatever is, we can drive this by 5 volt, and we can have amplifier to amplify the signal, because whatever it come out from the signals, right, is very small. All right, it's in microvolts. Or even smaller. So basically what it does is we need an amplifier circuit to amplify it, and also to actually by doing amplifier, but at the same time we can convert that signal into a table into a square wave. Right. So basically it's like a processing of that signal from the sensor and make it more useful data. All right, basically. So you can see that over the left hand side, right, is a block that we have some different level of hierarchy. So inside this MR sensor, right, this block here, there is some driver circuits inside there. All right, then we have the amplifier. We actually build the amplifier circuit, and actually can be block it and make it a library or whichever that you want, and plug it inside here. So basically you can actually have different level types design inside Simplora as well, right, to drive the circuits, to drive the sensor. And when this sensor is built, right, you can actually put into any applications, like, can be a speed control, can be doing some other type of sensing applications, as long as you know how to what is the environment like. For this case, right, it's a wheel, so we can have mechanical wheel load inside Simplora to and we can actually build the amplifier circuits, right, to rectify the signal into the controller. So this controller is actually a board diagram to control the speed. Then after me, we have a feedback loop that can build that. So basically, you can see that you are designing the sensor, but you can actually build them into a system level to control your sensor and see what is the characteristic and performance of this sensor inside a real system. And the next one is a flux gate sensor. And I'm not going through this theory of how does it works, but basically it's more on the tools itself. Excuse me. So flux gate sensor is basically make use of this linear response characteristics of this saturation between the pH curve. So it's actually through and flow of this pH curve, right, from linear point of view can be like at the higher inductance or lower highest inductance or lower inductance between the saturation. So the sensor drive between this region, all right, of the linear and saturation region for this pH curve. And this is just a basic for this flux gate sensor. So when this thing runs, right, basically what does it change is the inductance. Right, the curve shifts due to the external field. So when there's an external field passing through this device, right, this sensor, right, there'll be a change in the shift in the inductance. So when this inductance shift, right, we know that there is a magnetic field passing through. So it depends on the strongness of this magnetic field, right? There will be different shift level, right? So from there we can do a data processing. You know, what are the requirements from the, you know, how to process the external field into the real data. So you see here, right? When you put this inside Simflora and you do a flux, this flux gate sensor is actually done in Maxwell. So we can actually plug in on this driver circuit again, and we can plot this out inside our system. So we run this and you plot it out, and you can see that you know, the basically the distorted is is caused by the transient of this pH curve. All right, then basically the positive and negative parts are equal. So you can actually do it's like a calibration. All right, initial part of this sensor would be looking something like that, right? When you put a sensor response of 2.5 volt and 100 kilohertz of sinusoidal wave, AC signal. All right. So you will actually, when there's an external field there, all right, when the external field is 0, so what it does is it pick up this signal, right? It pick up this signal. So this is like a reference signal. I'll say that it's a reference signal or a calibrate signal. So when this magnetic field changes, right, from the external source, right, you will see that you can plot it out and you can see different type of magnetic change. And you can see that the positive and negative region are no longer equal. Before that is equal, no longer equal. So when these are not equal, right, so from there we can analyze what is the difference between this you know, reference and the ones with the higher flux and different higher field and higher magnetic field and lower magnetic field. All right. So from there we can actually analyze this. So it depends also on the current sense response, right? How you import the current inside. You can also import a response of 1.5 volt with 100 kilohertz of square wave, and you get something like that. You know, so when you see 0, right, basically it's a reference. 0 is when there's no external field. The red color one is actually 0. So if you see that when there's a 20 and minus 20 flux density, right, then you can see that the plot is different, right, for the green and the blue. Right, so this is how you differentiate that type of signals that passing through the flux gate sensor. So we can have we can connect up as a differential configuration as well with 2 sensor, and you know, with 2 sensor going through an integrator to integrate that signals and go into a low pass filter. So this basically, well, when there's no external field, right, it's always a calibration type of thing. All right, you can see that the differential signal is actually in the initial part is very high, then slowly it will start stable off. All right, so when there's a change, you know, in terms of the magnetic field, right, okay, so on the 2 milliseconds it start to change. All right, so basically you can see that from there you can analyze the common input signal and the differential signal, which is the green color and the red color. So I think this is my last slide. Basically, what I'm trying to convey the message today is Ansys do have solutions for all these sensors, all right, regardless of low frequency and high frequency. So high frequency basically is just, as I mentioned, it's just to analyze the antenna, all right, and antenna can be actually power up inside the system level simulation as well. As what you see here. The only thing is the HFSS is replaced if you are doing high frequency resonance type of what we mentioned, the waveguides and all this different type of cavity type of sensor, right? What you can do is you just put your model inside HFSS, all right, and this HFSS will be replaced inside model with this system level. So depending on how you power up that structures, right, you can actually do it in the system level as well. So the concept is the same, it's just different solver. Okay. So actually, you know, we have some. What I do here is actually we provide some examples. All right, and this sensor can be, of course, the sensors that I mentioned is used for speed, position, and phase sensing. Optimization and coupling physics solution can be done. This is not mentioned here, but we have, you know, if you guys are interested, we have solutions that actually putting this into thermal and stress, because it's not, you know, when you do a system level, it's, you know, it's just a system level. It's in ideal condition as well, right? But all the sensor can be installed, as I mentioned, it's installed in a very drastic environments like high temperature or low temperature, or inside a water or whichever, you know, which can actually affect the performance as well. But, you know, we can actually couple them and see what is the effect, you know, in terms of thermal and also a stress. All right. So basically that can be coupled into different physics. All right. So basically it's like multi-physics style simulations. So both components and system level simulation are necessary, right? Because we used to just do components simulations. You know the components so well, you address the performance of components, but by most of the time when your customers buy the component and put it inside the real environment testing, right, it's always out of specs, right? Meaning that the components doesn't work, or the components doesn't fulfill the specification inside the system level. So you need to do a system level. So most of my customers now, they actually do a system level simulation to make sure that the components works in a real environment. Obviously, it's still a simulation with the system level, which you can actually not just ideal, but you can put in the worst case as well. It depends on how you connect up that driver circuits or whichever external driving to drive your components, right? That one you can actually do a very constrained one as well. And even though you can actually put into a thermal to see what are the what is the performance like when, you know, when they are in a very constrained environments. So in that case, right, you know, there will be not many returns, right? Because most of the time when the customers will on your device and put in a real system, right, and it doesn't work, and there's a lot of return and all that stuff. So basically, this is to avoid the cost of returning as well. All right, to make sure that your performance of your sensor works inside a real environment that your customer wants. So with this, I end my presentation.